Elimination of contaminants in the environment around us has always been critical in modern humanity, even more so in the midst of a pandemic. Harsh chemicals can provide some of that protection, but aren't always practical to apply, cost effective, or necessarily safe. Could ultraviolet technology advances in solid state lighting allow electrical engineers to forge a better path for our health? As we're continuing to look for new ways to keep the environment around us and our loved ones safe and healthy and germ free, we're looking at new technologies and new ways that we can use lighting to eliminate the germs in the atmosphere around us. There have been some great advances in UVC lighting technology, ultraviolet C, that have allowed us to use solid state LEDs in this area to keep things like the surfaces in our kids' classrooms, the air that we breathe through our HVAC systems, and even the water that we drink in some ways free of many of these germs that we're trying all to stay away from to keep from getting sick. Today I have the privilege of speaking to Patrick Durand. He's the Worldwide Technical Director for Future Lighting Solutions and, quite frankly, one of the leading experts in LED technology around. Patrick, I've known you for a long time. Great to talk to you today. Really appreciate you taking the time.
Thanks for having me.
Absolutely, absolutely. So let's talk a little bit about this UVC LED lighting and where it's going. You know, we've seen UVC technology around for a while, but is it something that's just taken off lately with COVID, with the pandemic, or is it something that you've seen in the industry for a while?
Well, we've been investing in UV LED technology for over 5 years. So, we're investing in tools, we're investing in the technology itself. How do we define a system? How do we work with customers? What the pandemic did is just accelerated things, created this initial excitement from the engineering community in terms of how they can leverage this technology. But what I can really say is that it resembles what the general lighting industry went through 2 decades ago. Whereas the first step in terms of what we were trying to do pre-pandemic is just educate people, because the incumbent technology for UV has been lamps, so low pressure mercury lamps. They've been there for a very long time. What's new is the solid state lighting portion of it, and what we needed to do is start that education process. So how do you compare LEDs to lamps? What are the advantages of LEDs over lamps? Where does LED technology still need to make some advancements in order to be the dominant light source in this space? But truly what the pandemic did is that it changed the focus from trying to convince the engineering community that they needed to be educated to where the engineering community wanted to be educated in order to develop new ideas, new applications, and really solve solutions that in reality affects humanity. And that's where there was a lot of passion, a lot of excitement in terms of actually having an impact.
Absolutely, and I think we're certainly seeing that interest just has continued to grow enormously over the last 2 years, and I think we'd be wise to continue to invest in that, and invest in that understanding and that knowledge from the electrical engineering standpoint, and continue to work with designers on how they can implement this technology and the things that they're doing. Can you talk to me a little bit about the efficacy of this? I mean, certainly, UVC's been around for a while, and like you said, different forms. But how exactly does that work as a germicidal technology? How is it killing the germs? What's the actual process and scientific process that's going on there?
Yeah, so the key issue with LEDs and where there needs to be the most work is to increase the efficiency of the LED itself in terms of converting the electrical energy into light. Because when you work on a project, it's essentially what you need to answer is, what pathogens that you're targeting, how much time do you have to inactivate it, and to what purification level, meaning is it 99%, is it 90%, is it 99.99%? And all of that will have the impact on how many LEDs you need. Because the key thing in terms of the lamp technology, you have more light than you know what to do with. It's because you actually, for the SARS-CoV-2 virus, you actually don't need that much UV light in order to inactivate it. Because what the UV light is doing to the pathogen is that it's penetrating the wall of the DNA to the point that it disrupts it where the pathogen can no longer reproduce. And the amount of dosage or the amount of light density with time, you actually don't need all that much. However, the difference between the LED technology and the lamp technology is that the LED technology is much more expensive. But what you do have is a lot more flexibility because you can change the shape, you can have instant on, you have a lot more flexibility to make use of those photons, but those photons are more expensive. So it's very important to not over-design with UV LEDs, which is why it's very important to define the application requirements very precisely, because you do not want to over-design because it'll be too expensive.
Yeah, you don't want that inefficiency and cost inefficiencies in your system for sure. So what's kind of enabled this? Because it has been lamps for so long. Now we're talking about solid state LEDs, and right now maybe the cost is a little bit high, but as we saw with LED technology 10, 15 years ago, that came down significantly. I assume that will probably happen here with UVC. What's really been the advance that has allowed us to get to a point where we can start replacing those lamps with UVC today?
Right, there's really two elements. Number one is the efficiency of the UVC LEDs themselves. Right now on average, you can think that it's about 20% improvement in UVC LED efficiency per year for on average across many vendors. And when you compare that with the general lighting LED, right now we're in the 2% range of improvement per year. So it's basically an order of magnitude greater. And so right now, I'd say the average efficiency of a UVC LED is in the 2% range. So it's not a lot. However, this year in 2022, we're going to see the first UVC LED that will be 7% efficient. Oh, nice. And not only that, we've seen roadmaps for some of our LED vendors that actually are showing double-digit efficiency over the next couple of years. So we're going to see a tremendous amount of improvement over on the UVC LED side, and that makes a huge difference. It opens up new opportunities, new possibilities that were not available today, because the lamp is pretty efficient. Now the lamp has weaknesses in terms of that ramp up time. Turning the lamp on and off significantly impacts the lifetime. So there's a lot of drawbacks with the lamp. Obviously, there's the mercury aspect of it as well, right. And if the LED can be more efficient, then it's just going to open up the door. The second element is lifetime. So with UVC rays, it really impacts the lifetime of the package around them, and there's been a lot of effort to improve the lifetime of it to the point right now with the UVC LED. It's typical that you can have 10,000 hours of lifetime. So that's normal. And on the high end, you can have multiple tens of thousands of hours of lifetime with some UVC LEDs, which is significantly better than most UVC lamps. So there's already an advantage from that standpoint. And so then that again, it's about having a technology that meets the needs, because UV LEDs, you can target so many applications, and it's what's going to be important is choosing the applications that are ready today, and then planning in terms of with the efficiency gains and other technology gains, what applications are going to be ready so that you can hit the ground running, start planning for it. So by the time that you're finished the design and you've gone through the whole process, the LED technology is there so that you can leverage that opportunity with perfect timing.
Yeah, and so what are some of those applications that you're seeing? I mean, I mentioned a few in the opening, but where are you seeing that today moving to a solid state UVC LED is the way to go? It is where engineers should be looking to take their design in that direction.
Yeah, so there's a lot of applications that are ready today, and that we've seen many companies launch products with UVC LEDs. So as an example, HVAC, that's huge. And HVAC can mean a lot of things, right? So there's the air purification, but there's also the air deodorization as well, where you can actually leverage UV technologies to actually convert VOCs, carbon-based pollutants, odors, into essentially water and CO2, so that you are essentially at the molecular level deodorizing the air. So in terms of some air purifying units, they're using a combination of UVC LEDs to purify the HEPA filter and to actually purify the air, and deodorize as well to create very effective systems. You could do room level air purification, because we got to also remember, the SARS-CoV-2 virus, it's airborne, right? So, so it's not just at the surface; it's airborne, and a lot of pathogens are airborne pathogens, and so there's a lot of HVAC, room level HVAC products where essentially you're sucking the air into this contraption in the ceiling, and then UVC light is actually purifying so that it's actually practical for the people that are in the room. So if there's airborne pathogens in the room, you can actually directly purify the air. In an extension of that is upper room air purification, where the UVC light is actually being directed in the upper room, so in the ceiling area. So it's safe for people because the UV lights are actually not hitting anybody. Right. And so and you're purifying the air, and again, you're directly affecting the people that are in the room in a good way, meaning that you're purifying the air. In terms of centralized HVAC systems, in terms of cooling coils. So when in the summertime, if you smell that musty, humid smell in the air conditioner, well, that's mold and bacteria growing on the cooling coils. You can just leverage UVC lights on those, and it's inside the system, so it's completely safe to actually purify the cooling coils. Now, other than HVAC, of course, surface purification is huge. So in this case, this is where, in a room where you're actually shining the UV light downwards, this is where it's important to have sensors so that this only happens when the room or the classroom, because we're seeing a lot of school boards incorporating UVC lights as part of the program. So it's important to have timers, to have sensors so that it can be safe in those sorts of environments. We're starting now, because of the efficiency gains in the LEDs, we're starting to see UVC robots in a hospital setting, where traditionally it's been only with UV lamps, but now the UVC LEDs have gained enough efficiency that's making it interesting. Water, this is huge. This is, the whole, there's much more potential in water purification than anything else. So right now, obviously stationary water is what you can do in terms of dispensing water for any water dispenser. You have lots of water tumblers right now that were to have a UVC LEDs on that in terms of smart water tumblers. It's amazing. Now what you can also do in terms of running water, in terms of basically watering your faucet. The UVC LEDs of today can handle maybe 2 to 5 liters per minute. So we're not yet ready for municipal water treatment, but in terms of point of use, it's there, and the technology is perfect because it's the small size, it's the reliability, it's the robustness. We're also starting to see UV LEDs used in transportation, so on buses for air as well. We're starting to see them in cars as well for the air deodorization and air purification. So we're starting to see them pretty much everywhere. And the key thing is deciding where's the greatest fit for the technology of today, or where it's going to be a year or two from now, so that you can plan for that. And this is where we come in terms of providing that information in order to create designs that leverages the most out of the technology.
Yeah, no question. Our FLS team is best in class. I think you guys have been leading the way for 20 years in a lot of ways in all LED technology, and I have no doubt you guys will continue to lead in this technology as well. So I guess that kind of brings up the next question of, as an electrical engineer, if I'm starting a new design with UVC, I know when I used to do a lot of the high brightness LEDs in that kind of design, I was spending a lot of time on the thermal aspect and making sure that my LEDs were not overheating, and getting a metal clad PCB, and the optics had to be just right, and making sure I had no hot spots in my design, things along those lines. There were a lot of gotchas that I didn't expect when I first started LED designs. What are some of the things that engineers need to be considering when they're starting a new UVC design that you would recommend?
Okay, so you mentioned thermals in general. So in general, in the general line, yes, thermals are very important. But on the UV side, it's even more critically so, because generally the general lighting LEDs, so the white LED is very robust when it comes to temperature. UVC LEDs, definitely not as much, because lifetime has been the critical concern, and heat has a major impact on that. So thermal management will be absolutely key, because you're going to need to keep that junction temperature much lower than you would for a traditional LED. The other element, which is not discussed a lot on the UV LED side, but it's absolutely critical, is that the VF range, the forward voltage range of the LED, is much wider than that of a traditional LED. So when we're used to, particularly on the mid-power side of things, we're used to doing series parallel arrays of general lighting LEDs with no problems. Well, on the UVC side, that's very dangerous, because you can have ranges of multiple volts from LED to LED. And so therefore, you're going to need to, as much as possible, use, from a driver standpoint, use multi-channel drivers, or have long series strings, or have extra current balancing circuitry in order to manage all of that. Optics, once you go below 365 nanometers, the same materials won't work anymore for optics. So generally speaking, now some silicone materials are compatible with UVC, quartz glass, but that gets to be very expensive. But on an optics side, it's also very different. Now, the principles are the same in terms of, you can focus the beam to where you want, but the materials and how and the optics that are available are completely different. So that needs to be taken under consideration.
Absolutely.
And of course, from a design standpoint, we've built all the design tools in order to facilitate and accelerate this, because the fundamental question that we need to answer is, how many LEDs do you need in order to reach that design target? And when we first started talking to customers, no one knew how to answer that question. And we invested a lot of time and a lot of resource in order to develop these engineering tools so that you can answer those questions in minutes. Whereas customers would traditionally take weeks and weeks and weeks just to get an idea, but not with the confidence that is required. So they're always second guessing themselves. And we have those engineering simulation tools that will get straight to the point and get the customer to build that initial prototype.
Love it. No, and that's invaluable, definitely. What about, if you're trying to make the decision, because, again, kind of going back to my old illumination LED design time, there was a decision and kind of an inflection point on, do I buy an off-the-shelf, pre-built LED array, or do I go with my own chipped down LEDs? Is there kind of that inflection point with UVC as well?
Yeah, we're seeing a lot of customers choosing to go with the level 2 boards, so standard boards. Right. But it depends on the application, right? So we pride ourselves in terms of providing our customers options. So what we've done is that we've defined various standard boards of different shapes and sizes. To at first rate is that it allows customers to evaluate the technology without having to wait a month or two to get to play around with the technology. So we accelerate it that way. But also these boards have also been developed to match standard off-the-shelf optics as well as an optics arrays. So if the customer wants to accelerate things and those standard boards meet the requirements, we can go down that path. Furthermore, with our suppliers and our partners, we can also develop custom boards as well. And we've done a lot of those as well. If the customer simply wants to purchase LEDs, that's also an option. So it really depends on the capabilities, the timing that the customer has, and essentially what their objectives are, and then we can help to facilitate that and be flexible, which is very similar to what we're doing on the general lighting side. But what I do have to say as a major difference is that, unlike the general lighting side, for many of these customers, this is the first time that they've worked with solid-state lighting technology. So they've never had to develop a board before or work with an LED board before. And so there's that education process that we're going again through with the customers, and they're very appreciative because they can leverage the multi-decade experience that we have in solid-state lighting.
Yeah, no doubt. And there's a lot of gotchas when you don't have that experience, exactly. For sure. So that's a tremendous value there. And then I guess, the last thing I think that we've got to obviously consider as engineers is what's the safety to our end user. From an ethical responsibility standpoint, that's always a consideration for any design that we do. When it comes to UVC technology, what are the safety considerations that an engineer needs to take into account?
Okay, so first and foremost, from a UVC light or UV light in general, there is no such thing as safe UV light. So it's not a safe light, period. Mm-hmm. However, there are safe UV LED systems, and it's about the maximum exposure time. Now, what I also want to say in the same breath is, UV light and UVC light, it's not radioactive, right? It's not, oh, I've been hit by light, I need to go to the hospital immediately. There is a maximum, and if there is an overexposure, a burn, so if you get an overexposure in your eyes, within 2 days you will heal. So a one-off incident is not the end of the world. It will sting, you won't like it, and you don't want to do it again, but there's no permanent damage for rare instances of overexposure, and on your skin as well. And one of the reasons is that although it hurts and it's not fun, the UVC light does not penetrate deeply in your skin. The most dangerous light in the world is UVB light. That penetrates the skin and that can cause cancer. So UVC light is, again, it's not safe, but you can create UVC safe systems. Now, one of the elements is UL, as an example, because every product that an engineer or a company develops needs to go through the UL certification process. Well, from a consumer standpoint, UL will not certify any UVC product that is where you can expose the light to skin. So when you saw all those UVC wands, those are not legal. So UL will not allow those. Will not do anything remotely close to that. They will not approve those. Now, for the example when I gave from the school standpoint, well, that's a commercial application. So there needs to be rules, there needs to be a process in order, how do you make it safe? All the components that are there, how is it, all the redundancies in order to make it safe. But for consumers, it's a no risk element. So from a consumer application, if the UV light is in the box, and then if you open the box, there's no way that the UV light will turn on, then that can be approved. But something like a wand, UL will never approve those.
Right, gotcha. So something definitely to keep in consideration. It's not the kind of light you want to have in the ceiling of your kindergarten classroom on all day long. That probably wouldn't be a good idea. So, for sure.
Yeah.
Great. Well, Patrick, this has been incredibly insightful. Thank you so much for giving us an idea of exactly, how engineers can use UVC LEDs and where this technology is going. I think it's incredibly exciting how rapidly the efficiency of these solid-state LEDs is growing, and I think that's only going to accelerate from here as this becomes a more and more important technology for us, and really exciting to lean on your expertise and learn from it as always. I appreciate the time. If anyone has any questions or any needs when it comes to UVC LEDs, we at Future Electronics would absolutely love to help you. The Future Lighting Solutions group that Patrick heads up would love to get involved with you and provide their expertise in the designs that you're working on. Please reach out to us at Shaping the Future, one word, Shaping the Future at futureelectronics.com. And our engineers would love to speak with your engineers about how we can help with your designs. Patrick, again, thank you so much for your time today, and all the best.
All right, thanks, Todd.